What's up, everybody? So what we're going to be doing today is we're going to be talking about IP addresses. Now, if you've ever used a computer before and you're anywhat familiar with IT, you probably know what an IP address is. But I want to take this a little bit deeper in theory on why we use IP addresses, what types of IP addresses are out there, and talk more about protocols and how IP addresses are actually designed and made up. So I'm here in a Kali terminal, and I'm just going to type in a simple command, and that command is ifconfig. Now, if you've used Linux before, this might be familiar to you. If you used Windows, it's similar to ipconfig. All I'm trying to do is bring up my IP address. So what we can see here is that we have an IP address, which is our inet. This is my IP address here. I also have another IP address, this inet6. This is what's called an IPv6 address. So we've got this inet, which is considered an IPv4, and this inet6, which is considered an IPv6. Now you can notice right away that there's two different types of notations for these. This inet here is in a decimal notation, and the IPv6 is in a hexadecimal notation. We'll get to the importance of that in just a second. So when it comes to IP addresses, this looks probably pretty familiar to us. This is an IP address. This is how we communicate. We communicate over layer 3. And you're going to hear me talking about layers repeatedly throughout the course, or at least throughout this part of the course, so that we can get familiar with how we're actually doing this. So I want you to be familiar with troubleshooting these layers, and these layers all refer to something called the OSI model. So when we talk about layers, we think about the OSI model, and I'll introduce the OSI model here in a few videos, and it should all click once I introduce the OSI model. So if I brought in the OSI model up front, it might be boring, might not make sense. So I'm going to introduce the OSI model near the end, and you're going to say, hey, yeah, that all makes sense. So what we've got here is we've got this IPv4 address, and this is the most commonly used format that we use today, right? We use IPv4 for mostly everything. And again, this is in that decimal notation. So when we see this decimal notation, it's just realistically a bunch of ones and zeros that are put together so that we have this human readable format. Realistically, all we're seeing here with 192, this first section here, this first octet, is actually just a bunch of ones and zeros. It's 8 bits. So we've got a range of 8 ones and zeros here. We've got another 8 here, 8 here, and 8 here. So when it's all said and done, this inet, or this IPv4, is made up of 32 bits, 8 plus 8 plus 8 plus 8 here, and which equals 4 bytes. So another way to think about that is to think about it as, say, something like this. 1, 2, 3, 4, 5, 6, 7, 8, period. Okay, that is one section there. So we've got 8 ones that can make up this, and then we'd have another 8, etc. I'm not going to beat a dead horse here. But I do want to give you guys another example. So if we go into our applications and we go to a text editor really quick. So the way this looks is something like this. We start with a number like 128. I'm going to try to space this out as best as possible. And all I like to do is think of 128 as my base. And this will make a lot more sense when we get into subnetting. So please, if you're confused by this, don't worry. This is all theory right now. When we get into subnetting and we get hands-on, it'll make a lot more sense, I promise you. So let's say we have ones and zeros here. If we have a 1 for each of these sections, and I'm going to space this out again as best as possible, it's not pretty. But if we have a 1 for all of these, this equals 255. Why does this equal 255? Well, you take this, and all these numbers add up, 1 plus 2 plus 4 plus 8, all this adds up to 255. So let's say if we didn't have all the ones and zeros, we had just some ones enabled, like these last 3 here. Okay, well, this would equal 7, because we have 4 plus 2 plus 1 equals 7. So our first number, or whatever number this applied to in the octet, would be 7. So if we had 7.7.7.7, it would just be this numbers repeating over and over, these numbers repeating over and over, right? So be 0000111.0000111 and so forth. So this is kind of what it looks like behind the scenes, because again, a computer is just ones and zeros. We're all binary. So what we're going to do is we're going to close this out. And we're going to talk a little bit of other theory when it comes to this, and why INET or IPv6 and why IPv4. So let's close this and let's talk about IPv4. So I'm going to bring up a calculator. And with IPv4, we have these 32 bits. So what we can do is we could take 2 to the 32nd power, and this is the possible amount of IP addresses that we could have. So we have somewhere in the 4 billion range of IP addresses. Well, spoiler alert, we don't have only 4 billion people on Earth, right? We're up to 7 something billion at this point, and all these IP address spaces are gone. So IPv4 has been around since 1981. Nobody thought we were ever going to use all these addresses. Computers weren't really a thing. Who knew that we were going to want all these addresses? And, these companies started buying them up, and they started buying them up in large chunks. And then they sold those to ISPs, and then ISPs sell those to you. And so these IP addresses have been gone for a very, very long time. And chances are when you have an IP address and you get this IPv4, you're only going to get one. If you're a corporation, you might buy more. But we've run out of IP address space. There's just not enough to go around. So the theory is, okay, let's come up with something different. Let's come up with IPv6. Now, this hexadecimal is actually in 128 bits, which makes things just a little bit longer and adds quite a bit. So let's take this 2 to the 128 power. And we get a number that I cannot tell you how to say. Not even going to try, but I can guarantee you that in our lifetime, we will never use this address space. So we've come up with the solution of IPv6, but nobody really uses it. IPv6 is just a thing that's there, but when we get IPv6 addresses assigned, but still to this day, everybody's using IPv4. Well, how is that possible if we're using IPv4, but we're out of address space? Well, think about this. We're using something called NAT, which is Network Address Translation. Now, let's think about your network. So you might have a cell phone or computer or multiple devices. My network has at least 20 devices on it. I've got cameras, I've got multiple cell phones, smart TVs, everything that connects to my internet gets an IP address. And that's 20 IP addresses right there, right? So let's say I have 20 devices, that's 20 IP addresses. Am I taking up 20 IP addresses out of that 4 billion? No, we're actually using something called Network Address Translation, or it's called NAT for short. And we'll talk about this again when we set up our actual lab. But with NAT, what we're doing is we're assigning these private IP address spaces. So we've got this 192.168.57.139. Now, if you've ever seen a IP address before and you've been on a network, good chances are it probably started with 192, or maybe it started with a 10 dot or something along those lines. And that's because those are private IP addresses. So anything that starts with 192.168 is not an IP address that is going to be out in the interwebs. It is going to be an IP address that is only known to you. These are called private IP addresses. So because we use these private IP addresses, we can pass them out through what is called a public IP address. Now, to make better use of this, let's go out to Firefox, and I've already got a tab open. So I went to Google and I just said private IP addresses, and I clicked the second image here because I think it's a great image. So if we look at this, there are classes of IP addresses, private IP addresses. Now, there is a class D and E. We're not going to worry about those. The big three are class A, B, and C. If you know these, you are good to go. So if we look at class C, this is what the most common household and small business use. So we see it starts with the 192.168.0.0. So the 192.168 are constant. If you see a 192.168 address, you can guarantee yourself that that is a private IP address space. And then we have the range of changing this number between 0 and 255 and this number between 0 and 255. Why 0 to 255? Well, that'll all make sense when we get into subnetting. But what that allows us to do is have a large number of networks here and a small amount of hosts. But for a regular user like you or I, or a small business, 254 hosts is pretty good. I mean, I'm only using like 20 in my household. So the most common household is probably using this 192 address. But what about a big business, right? Something huge. Okay, well, they might use a 10 address because a 10 address frees you up to anything after this 10 is private. So 10.1, 10.1.1.1, whatever you want to put in here up to 255 on each octet makes for a small amount of networks, but a large amount of hosts. Okay, and don't worry about the host versus network thing. Again, subnetting, we'll talk about that. It'll all make sense. But just imagine the amount of hosts that you can put in here with this wide range. So because of this, you'll see larger corporations using 10 addresses. You'll also see a lot of corporations, even small businesses, using 10 addresses. The matter of fact is, as long as you have this private IP address, you're good to communicate across your network. So any IP address outside of these and the loop back here are free game for the public address space. They're probably already owned, and you purchase those or rent those really from your ISP, your internet service provider. So going back to this thought, we have a Class C address. My network's Class C, 192.168.57.139 here. So it falls into that Class C. I've got all these devices on this 192.168 network. All these devices are talking out of one IP address. That is my public IP address. That is what I rent from my ISP. And all of this network traffic goes out one IP. So this is how we have achieved or solved the issue of running out of address space without having to use IPv6. Not that there's anything wrong with IPv6. It's not pretty. I mean, it's way easier to type this stuff in than it would be to type something like this in. But at the same time, this is how we've solved it. We're able to still use IPv4 in mostly all networks, and we are able to communicate out with this quote-unquote IP address shortage. So hopefully that makes sense. We're going to build upon these concepts. Again, IPv4, IPv6, IP addresses are layer 3 protocols. Layer 3 is a router. So when we route traffic, we route via an IP address. So we're going to build upon that as well as we go in. Hopefully this is all just a refresher to you. So that is it for this video. I'll go ahead and catch you over in the next one.